Hi and welcome to Bytes and Bits. Elecrow recently released a new LCD panel with a built-in ESP32 microprocessor on the back of it. Now the difference with this panel to normal sort of microprocessor ones is that it actually uses a very fast 16-bit parallel RGB interface to interface the ESP32 and the actual screen itself. So the upshot of that is that we should get a very fast data rate between the microprocessor and the LCD panel, which should give us some very good performance on this large 800 by 480 pixel display. So in this video, I want to have a look at the actual device itself and see what it involves. We'll then have a look at how well it performs and how we can optimize that performance then to make sure that the drivers we use allow us to create some really good projects using this as a display, either as a control panel or perhaps as some other sort of game display or so on. So let's start by having a look at the actual device itself and see what it can do. So the display unit comes as a single item with the ESP32 circuit board mounted on the back of the actual LCD panel. So power is via a single USB Type-C connector, which also serves as the main USB port to connect to our development system. Or you can use it, of course, as a separate USB port whilst your system is running. Now the processor on this board is an ESP32S3 with a dual-core 32-bit L6 microprocessor that can run at up to 240 MHz. It also has integrated Wi-Fi and Bluetooth wireless functions like most other ESP32 units. Now this particular processor is teamed with 512K of fast static RAM backed up with 8 MB of almost as fast pseudo-static RAM, or this PS RAM, that's running over this fast SPI channel. Now the ESP32 also has 4 MB of built-in flash storage, but it also has an SPI connected SD card reader that we can use then for some mass data storage. Now around this board there are a number of I/O connections. So we have 2 UART ports for serial communications, along with a single GPIO output. Now this single GPIO output is probably the weakest area of the board, so you won't be able to connect lots of different buttons and devices to the screen without resorting to using one of the UART channels for that connection. Now we also have a battery connector with battery management circuitry, and that will allow you then to plug in any of these LiPo batteries, and it will actually then power that and recharge that from the main USB power input. Now there also is an I2S driven speaker output, and that allows us to get some sound out of the board, and that's taken down to this little 2-pin connector down here. Now the touch panel on the device is a capacitive touch screen. Now it doesn't support multi-touch, but it is actually quite accurate and responsive, and that will actually make this unit ideal as some sort of control panel for one of your projects. And with the price of this unit coming in at around about £40 or $40, this does represent incredibly good value for money. So when you first power on display out of the box, it will start to run a demo application that shows its compatibility with the LVGL control panel software. Now this software is a very powerful user interface building tool that allows you to create very professional level displays with all the modern features you'd expect, such as scrolling panels, touch controls, graphical instruments, and so on. And all of these interfaces can be created and hooked up to your code using a free for personal use version of their development software. Now I'm not going to be going into the use of this tool in this video, but it is well worth a look if you want to put a great user interface onto your project, and I probably will cover this in a video later as it is a very powerful tool. But for this video, I'm actually going to look at the performance of the LCD panel as a standard display for our projects. So the big difference between this unit and other ESP32 LCD panel combos is the way that it actually interfaces with this LCD panel. So there are a range of ways to interface an LCD panel with your microcontroller, and an SPI is a very common method where your ESP32 talks to the LCD controller chip using a serial communications protocol, And commands and pixel data are sent over a simple 3-wire interface, and you're able to create a very acceptable video output on smaller resolution LCD panels. But the downside of this serial channel is that it is slow and it does transfer single bits of data at each clock cycle on that bus. So this method, of course, can restrict the resolution of the panel that you can sensibly control with a microcontroller. Now, the RGB interface used in this panel has a 16-bit parallel data bus, which is the main reason why we don't have so many I/O connections left over from our ESP32. Especially when you also consider that you're going to need a few clock lines and control lines to control the LCD. So with the driver chip using the standard 16-bit pixel color data, we therefore send 2 bytes or 1 complete pixel of information per clock cycle on the bus. Now, the driver chip allows us to display graphics on the screen using the standard range of primitive drawing commands such as pixels, lines, boxes, and so on. Or of course, we can send the display data over as a screen area data dump, which will allow us to fill in an area on the LCD panel in one block. Now, to do this, we can use frame buffers in our code and then use DMA channels to perform the actual sending of the data over the interface. And all of this then adds up to give us a very streamlined system for getting the display data from the ESP32 onto the LCD panel. So if we run the interface at its maximum stable frequency of 15 MHz, this actually gives us around about a frame rate of 35 frames per second. At least this is the theoretical frame rate that our 15 MHz bus should give us. And of course, that doesn't allow for various sort of timing and control data being sent. One of the problems sort of with this interface though is that this RGB interface isn't supported by all of the LCD driver libraries that we would normally use in our Arduino and ESP32 based projects. So in this video, I'm actually going to be using a library called the Lovyan Library, which is actually the one that's suggested by the Elecrow sample software. So the sample software that you get with this screen can be downloaded from the Elecrow website, and it includes a number of examples for how to drive the screen, the speaker, the SD card, the touchscreen, and various other bits of the hardware. Now, to get the driver to work, we do need to set up a few class objects that implement parts of the RGB interface. So again, this is all detailed in both the Elecrow samples and the driver library code. And I do admit I did have to do a bit of work between those two, as both seem to contain some bits that we needed to do, but not the full picture for this particular screen. But again, all of my code I will make available to you, so if you do decide to get hold of one of these, you should get my full driver code that will let you get up and running very quickly. But I am going to briefly go through the setup here. But as I say, go through to that library, and also then do make sure you visit the bytesandbits.co.uk website and look at the project page for this particular project for more information out there. So the actual driver setup then is a bit more involved for this RGB interface. But once you've got it going, it's actually identical then to use the driver for our various projects. So first, of course, we have to import the actual library. And again, you can see on this particular example code here, we're importing our library and then a couple of extra objects that we're going to be using. We then need to create our own class that's going to inherit from the generic LGFX device class. And this lets us build up our LCD panel model that's specific then to this particular device. So you can see here that our code, we are creating a new class which inherits from the LGFX device class. And inside that, we're going to embed then a bus instance, a panel instance, and a light instance. So in our class constructor function then, we actually have to initialize these objects. So you can see here that the panel object then models the actual LCD panel itself, along with some of its parameters, such as the width and height. We then need to set up a bus class, and this sets up the hardware interface between the ESP32 and the panel itself. And you can see here that we're defining a range of pins to drive the various lines on our RGB data bus. And you can see here the data lines and the control lines coming through. And we also then, of course, do need to specify what speed we want to run this bus at. So again, I'm running it here at the full 15 megahertz. Finally then, we have a light class, and this allows us to control the brightness of the backlight on the LCD panel. So as you can see, the bus and the light objects are actually embedded inside the panel object, and that's then set as the main panel in the library code, so that we can now just simply use the main class methods, and the class itself then will use our definition of our LCD panel model to actually send the correct signals out to drive our display. So after the setup code then, we should now be able to draw on our LCD panel. So in this very first test sketch, all we're doing here is we're getting the code to fill the screen with a solid color and then pause before changing color. And this is just to show that our actual screen is, well, basically that we're able to talk to it and get it displaying some information. So in this next piece of code, we're again using this LCD fill screen method to fill the screen with a random color. But now we're going to start looking at the performance of the screen. So we're going to time how long it takes for that particular fill screen function to complete. So this method will send a full screen of pixel data to the panel as a single block write command. So it should actually give us our maximum full screen frame update rate at this particular bus speed. So as you can see from the code, running this task, we've got it to display how long it takes there. And this value, of course, is in microseconds. So it's taking us about 33,000 microseconds or 33 milliseconds to complete that fill screen function, which pretty much gives us our 30 frames per second at this maximum data rate. So this means that we should be able to animate our display by completely blanking our screen and then redrawing all of our screen objects, rather than having to draw a screen object, rub it out, redraw it in a new place, and so on. So let's try and add some animation and see if we can actually make that work. So in this sketch, we're going to be bouncing a number of boxes around the screen. So we're going to be clearing the display between each frame update. So the basic algorithm then is to update the position of the boxes. Then once we've got everything ready to render, we're going to clear the screen, render the boxes, and then loop back around again. So if we show this working then, as you can see, this does actually work, and we do maintain a great frame rate. So we're getting pretty much our standard 30 frames per second. But with all of these screen objects being drawn in real time, we are getting some strange timing effects happening here, where areas of our screen are starting to disappear, and so on. Now, the screen is obviously being updated as the code suggests, but I think this strange effect is probably down to our eyes and our persistence of vision, where we are catching areas of the LCD panel while they are in various states of update. So sometimes we're catching it when our eyes catching it when it's part way through clearing the screen, so part of the screen is shown as blank, and so on. And so this display, with it being continuously being changed with complete screen wipes, and again, these screen wipes then are taking up most of the display time. This is why we are seeing the image disappearing at certain intervals. So to get around this then, we actually need to keep the full frame. So once we generate the full frame, we actually need to keep that in view for a short time to let our eyes actually register that as a complete image. So we can add a short delay after the actual frame update is complete. And as you can see, once we run this particular version of the software, we now do get a nice, correctly viewed and not perfect, but a reasonably stable display. But of course, the downside here is that we are now adding in a delay in our frame redrawing cycle, so we are artificially slowing down our frame rate. And as you can see from the display, we do still get the frame being built in our sort of 36, 37 milliseconds, but of course we're now delaying for about a tenth of a second afterwards to stop the flicker effect. So if you are creating a display that doesn't need to update quickly and you want just a very quick and easy way of actually getting your screen up and running, then this screen blanking and then redrawing dials can actually work quite well. Again, if you're happy with your data being updated at this sort of 10 frames per second or less, and of course you are always going to get that slight flicker as we clear the screen and then start redrawing again. But of course it is a usable technique. So we do need to have a look at how we can improve this then, and the obvious answer is to use something called a frame buffer. So in this next step, we're going to use a memory-based frame buffer, and this is where we keep a representation of the screen in our system memory. We then do all of our rendering onto this memory representation, and then we send all of that pixel data as a single update to the LCD panel. So this should remove the flicker effect and this strange persistence of vision error that we're getting. So the Lovyan library actually has all of this ready made for us. So we have an LGFX sprite class, and that will do all of the hard work for us. So the class defines a block of screen memory that you can actually size to whatever screen dimensions you want, and then that can be rendered anywhere on the screen using a single block write command. So we can create a sprite here that is actually a full screen size, draw our next frame onto it, and then display that so that it actually refreshes the whole panel. And in this demo here, that's exactly what we're doing. So as you can see, we now get a correctly animated display with a nice steady output without any of that flickering effect. But if you look at the speed it takes, or the time it takes to generate a frame, you can see that we've lost a bit of speed in handling this sprite memory. So the extra overhead then of translating the sprite memory version, putting that out then to the screen, has taken our frame rate down to about 15 frames per second. So in effect, we've practically doubled then the time it takes to actually generate a single frame. But this method does allow us then to have complicated drawing routines, and we won't have that building up in front of the user as each individual element is drawn. We can actually do all of our rendering off screen in our memory buffer, and then just simply show the finished frame as one single screen update. Now this does give us a very usable technique for controlling our screen, and I think this is pretty much what the LVGL control panel software is doing in sort of creating a frame buffer and then being able to render full screen updates in that. And as we saw with the demo there, that does actually work very well. And probably if you looked at it, it was giving us around about this 15 frames per second update time. But we can try and optimize this a little bit further. So if we actually zoom in and take a closer look at a small region of our screen, if we actually look at these pixels that are changing, we can actually see that the majority of the pixels on our screen are actually not changing between frames. Mostly they are sort of fairly static and only changing them when in this particular demo, when one of the boxes passes across it there. So this does mean that a lot of the screen data that we're sending across our RGB interface for each of the frame updates is actually just wasted time. So what we should be doing is looking for these pixel changes between frames and only sending those over to the screen. And this way, we actually may only have to send, say, 10% of the screen pixels over the RGB interface, so that will greatly increase our frame rate. Now to do this, we actually need to do something called double buffering for our display. And this will let us have one buffer that represents what's currently on the screen, so in other words, the last frame that was rendered, and then one buffer which is where we're going to generate our new frame. And then when it comes time to send the new frame out to the screen, we can simply scan the differences between the old frame and the new frame, doing that row by row, and then sending over only the changed pixels. So in this code that I'm showing you here, we have a new function called diffDraw. So in this code, we're actually using two of these LGFX sprite objects, and then we're alternating them so that they, for one cycle, one becomes the current frame, one becomes the new frame, and then we swap them around for the next cycle. So when it's time to update the display, what we do here is we actually look at the pixel data for each sprite, going along each row of pixels from top to bottom. If we find a series of pixels which are the same, we simply skip over them and do nothing. But then as soon as we find that one of the pixels has changed between the old frame and the new frame, we actually mark the start position of that on the row. We then continue along our row and until we find pixel data that then starts to match back up again. And this then gives us a strip along that row of pixels which have all been altered between the frames. And that's what we actually then send across to our LCD panel. And then the process repeats itself. So we're now at a pixel which matches, so we carry along until we find a pixel that doesn't match, and then mark that block, and so on. And we go across every row and across every column. So if we run this bit of code and have a look at what we're getting, you can see that we actually get a really nice looking display, same as before, but the actual frame rate then gets us back up to around about our 30 frames per second that we had initially. So you can see there that we've made quite a big difference. So this particular difference routine here, to be honest, it's very basic. It is part of the Lovyan examples code. Again, I have modified it slightly to make it work with our particular display, but I have to be honest, and I didn't actually write it all myself. But as you can see, it's a fairly basic idea of what it's doing, just simply finding changed pixels and sending them across. So this particular method, as I said, is basic. It does rely on there being not a lot of change between frames. So it is just simply working on individual changed pixels. So if we have lots of changed pixels and unchanged pixels on a particular line, it will end up sending lots of very small strips of data. And if that starts to get a very complex display, it can actually end up increasing our frame drawing time as it sort of sends little tiny blocks of data across rather than one big block. But as I say, for most of the displays that you'll probably be working with, especially if you're using control panels and even a lot of game code, you will find that most of the screen doesn't change between frames. Either it's just simply sort of background images, or it's blank screen, or whatever. So this basic routine actually will give us in general, a very good improvement in performance. So this then leads us on to the final demo. So this is actually a demo taken from the Lovyan example page, which actually sort of brings together all of these techniques. So it's the bouncing circles demo. So this code does use the double buffer display driver, but it also starts then to make use of the dual processors inside the ESP32 to share the processing load of modeling the balls and updating the screen. So in this particular one, each of the balls is being modeled correctly. So the physics is being modeled correctly here with proper collision detection and collision reactions between the various balls. And there's also, of course, you can see here a background grid being drawn per frame, and that just adds some interest into the display. So as you can see, it does have a frame rate counter up in the top corner here, and so as our first balls come onto the screen, we're running at about 20 frames per second, and this then starts to drop off as the load, the processing load to calculate the ball physics and models increases. So the actual time to draw the screen doesn't particularly change, but we are now loading up the processor in actually modeling our code. But again, I'm really showing this here as an example of what actually can be achieved with our trusty little ESP32, and then using this 16-bit RGB interface on this Elecrow display to actually give us what I consider to be a pretty impressive piece of hardware, where we are getting a good frame rate. Okay, so it's not your sort of Xbox type 60 frames per second, but a good frame rate then for a full screen at our 800 by 480 pixels just from our ESP32. So again, if you were just running this as a control panel or even using some games codes, I think this display would cope fantastically well. So, well, that pretty much wraps it up for this video. So I have been really impressed at the speed and quality of this 7-inch display, and how it actually opens up then our ESP32 projects to being able to use this larger LCD unit. Again, I haven't really looked at the touchscreen, but that is fairly standard and just works as you would expect. And it gives us a display driver which allows us to run that full screen then at a very usable frame rate using some simple driver software, which has an interface which most of us will be used to if we've used any of these LCD panels before. So with it also being compatible then with this LVGL library, that does open up a lot of other use cases where we can build some very, very impressive, professional-looking, touch-enabled user interfaces. And I will be looking at that in more detail later on, so keep an eye out for that video coming up. So if you have enjoyed this video, do please click that like button and subscribe to the channel for lots of other making, coding, and gaming projects. I look forward to seeing you again in another video very soon, and bye for now. For more games programming, electronics projects, and retro gaming, please make sure you like this video, subscribe to my YouTube channel, and visit my website.